the deadline for today's report sent will be the Wednesday, 6 p.m. As you will see in the moment, this will be a brief report. Thus, I think this is the absolutely enough amount of time, so no worries. I would like also to remind you about today's midterm test, and this will start at 5 p.m. on the portal. So I will share the screen with you. Excuse me a moment. Can you see the STVD screen?
Yes.
Okay, great. And only the STVD, right? Nothing else.
Yes.
Okay. So the first question of the report are quite simple. This is about actually searching the documentation. Or maybe some introduction to the MCU clock. So actually the MCU clock generator generates the synchronizing source waveform for the CPU and its peripherals. This might be by using the external or the internal clock source. The generated signals from the forms the basis for the clock cycle, and also does the machine cycle. So the quick explanation about the MCU registers. Actually, at the beginning of our assembly program, we have the two basics clock register, and your goal is to name them. That's quite simple. And there is another one. I don't need it. I don't need this register to be here in code. But for you, it is the additional exercises to find its name. Also, except the name, beside the name, you have to specify briefly the explanation. What those registers are responsible for. Second question is the default frequency and the frequency source of our STM8L used in discovery board. Maybe some of you already know what is the default MCU frequency in our case. Okay, I know that it requires maybe a more deep look into the MCU documentation, but going further, a question about the external clock in discovery board. So it's about the reading the schematic and what kind of clock is that. So just to remind you, I will change the screen view now. Can you see the discovery board documentation now?
Yes, we can.
Yes.
Great. So by looking at this schematic, what do you think? Do we have a main clock source here or not? This might be tricky. And what is its base frequency?
32.76.
Yes, but this is the trick. This is not the main clock, but maybe you know how this specific clock with this specific number, how we call this clock.
It's a real-time clock.
Great, that's the correct answer. That's the real-time clock. So this is not the main clock, right? So
16 megahertz.
yes, that's 60 megahertz, but there's a specific note here. But the question was about whether we have this clock or not, if it's connected.
It's not fitted by default.
Yes, that's the correct answer. It's not fitted, and we have to always take a detailed look. So it's not fitted, and the another hint for that is this actually X2, right? You have the empty space and through holes for our basic clock and the footprints for its capacitors. But we also have our real-time clock, which is the different type of clock generator. So actually you have the answer for the report. It's we have a place in our board, but it's not fitted, and we will just go back to our code. So the question was, is there any external clock on discovery board? So the answer is no, actually. And what kind of clock is that? So if we do not have the external clock, it means that we have the internal clock, which is the RC generator. And actually, this is the, as I've mentioned, those are very simple tasks for the clocks. And maybe some hints about what sentence should be placed in the summary of as for the clocks. In the conclusion, just summarize the above information. The example partial sense like, for example, the discovery board uses the clock source, and you already know that this is the internal clock source. And the information about the MCU frequency, MCU base default frequency, and the default signal source can be found in, and there you can, or you even should add the reference to the documentation. And that's all for the clock part. Also, you can add the sentence about the advantages of using the external clock source over the internal clock source. And maybe some of you already know what is the advantages of using the external clock source over the internal clock.
The stability and accuracy is better.
Yes, actually, those are the basic reason. Stability, accuracy, and generally that's all. And now we can go further into timers and the interrupts. So we have only one program which represents all of our work during the lab. So actually, this code is about the same as what we discussed during our regular lab. So it's about LED blinking, but in this case by using the different methods. And as I've mentioned, in our case, these are the timers. So some basics information about the timers. The timers can be found for a variety of purposes, including time-based generation, measuring the pulses lengths of input signals, and this is called the input capture mode of timer. Generating output waveforms, which is called the output compare, and this will be the subject of our next labs. And also, what we're gonna discuss today, it's about the interrupt capability on various events. For example, capture, compare, overflow, and update. So we are going to use the timer 2 and its capability to send and interrupt when it's updated. Essentially, the timers are the counters, and the timer 2 can be used in its most basic way to count upwards from 0 until a specific value which we set has been reached. It is then reset back to the 0 and starts again triggering an interrupt at that time. The timers take their clock source from the main master clock, which we set here. But they can be also prescaled in order to lower the clock frequency that is counted. This is done for timer 2 by setting the lower 4 bits in the TIM2 PCCR register. And the initializing the timer 2 procedure is as follows. First, prescale the timer's clock by some number by placing into the timer 2 PCCR prescale register. This must be done by loading both the high and the low bytes separately, with the highest first as per technical reference. Then place the another number into the auto refresh register, TIM2 ARR. This is the value we count to before returning to the 0. Then enable the interrupts on the timer update. So we get an interrupt when the counter is updated, reset to the 0 after the time set above. Set the CEN bit on the timer control register first to enable the timer. Reset the CPU interrupt mask so interrupts are enabled with the REM instruction. And in our MCU case, we have to do the additional initialization. And this is this register. And I can give you already some hint to your report. This is called the CLK PCKENR1. So this is the clock for the peripherals. And maybe does anyone knows why we have to set up this register? This is not typically for every MCU type, but it is the common practice in low power MCUs. And just to remind you, our STM8L is the represent of low power family. And this is the common practice in low power MCU to disable as many functions as possible to allow the minimal MCU operation to reduce the MCU power consumption. Since the enable clock for any peripherals consumes a little bit of power, However, in low power MCU, developers fights even for a single microwatt. Mostly those kind of MCU are designed to work with the batteries over the long time period without a maintenance. Hence, there is a need to enable this this register because it's disabled by default in order to reduce the MCU total power consumption. Also, besides the timer initialization and your task in the report is to describe those register and what they are responsible for. I mean those 5 registers of our timer. And we have to set up an interrupt handler to catch the interrupt when it happens. In this interrupt handler, we toggle the LED state as we've done previously by using the delay function, for example, by using the no operation instructions. In our case, it will be more sophisticated because we are going to use the timers. So to use the timers and the interrupts. So some basics explanation about the interrupts behavior. Just give me a moment. I will find some friendly explanation. How does the interrupt work? Can you see the screen? Okay, so this is the interrupts explanation for everyone. I like this history. So our MCU needs to wash those dishes. So it means that it has some program to be done. Program is actually, as you know, the set of the instructions, which is proceeded by the MCU constantly. So during washing the dishes, our MCU can hear the knock from the outside, and this is called the interrupt signal. And in this case, the MCU skipped washing the dishes and went to open the door. And this is the metaphor that the MCU is starting to process the interrupt request. and actually it stops proceeding the main program. And in this case, this is the postman. In the MC world, in our case, this will be the timer update, but there are many different interrupt source, like for example the GPIO changing state, the analog to digital converter, like the serial communication, etc., etc. But in our case, this is the timer. So the external interrupt signal was a postman. The letter delivery was the interrupt goal. And the interrupt routine has been proceed. So the MCU is getting back to washing the dishes because it's received its mail from postman. And in programming, we can tell that the MCU returns to the last instruction, which has been left in order to interrupt handling. So having this friendly explanation, we'll go back to our STVD. In documentation, and I already know where it is, but normally we have to search for the MCU datasheet and the reference manual to find the proper number of our interrupt. And in our case, in this interrupt segment affected, this is in STVD case the last part of the main ASM. This is the interrupt number 19, IRQ and 19. Actually, this number is very important because if we want to use the timer 2, and we have to specify the exact IRQ number. However, this this interrupt directive can be named as you want. Of course, for example, as like the variables. I suggest to use some logical names, like in my case is timer 2, which is quite reasonable. And after specifying this interrupt vector, we can go to the interrupt handler, which is here. And in this case, all we need to do in the interrupt is to toggle the LED and return from the interrupt routine by using the IRET instruction. Then we will go to the infinite loop where the MCU waits for the interrupt. In our case, we do not nothing. And what do you think? If I will comment this line, will be able to compile our program or not?
Yes, you will be able.
That's correct. Because the wait for the interrupt instruction is just wait for the interrupt. The interrupt flag is cleared, allowing interrupts to be fetched, and the CPU clock is then stopped, reducing the power consumption of the microcontroller. So it's optional. So it's better to add this instruction in real world in programming our discovery board, but sometimes in the case of the debugging, we have to comment such kind of instruction referring to the interrupt, because they may cause the problem during the debugging process. And we have this RAM instruction. So it is called reset the interrupt mask, or we can also call it the enable the interrupts. So it clears the interrupt mask of condition code register, which enables the actually the interrupt possibility. So it's you can treat it as a switch, as an enabling switch. If it's present, then the interrupt are also present. And actually, this is the first task on your report. Explain the reset the interrupt instruction on the condition flag register. So you already have this this code on the portal. Please try to create the new project and exchange the default generated code by pasting only this this part without changing the mapping ASM and any other files. It should be able to compile and build and then do debug. To see the resets the interrupt instruction behavior on the condition code register or flag register. Actually, I've already mentioned what its influence, but all you need to do is to explain it by your own words. What is the interrupt source in our code? So, simple question for those who are listening. What is the interrupt source in our code? timer 2, right? And that's the correct answer. And based on the discussed code, briefly describe the following timer 2 registers. So this is your work to find their explanation in documentation. I've already mentioned about their what they are responsible for, but again, you have to explain it by using your own words in report, and by modifying which register we can affect on the LED blinking frequency. There are 2 registers in timer 2 and the one register in general. So maybe you know what is this register. By changing its value, we can modify the LED blinking frequency.
Would it be team 2 pre-scalar register?
Yes, that's correct. That's the one, because this is the pre-scalar register. The second one is this register ARRL and H, because here we are placing the value from we are counting down or up. In our case, we are counting down to the 0. And it's not the timer, but in general, this is the main clock pre-scalar, and this is this register. All you need to do is to find its name, and then its explanation in reference manual. And also the last question in the report: why we need to enable the CLKPCKANR register. So this is this register for peripherals, and I've already mentioned about it. So we have to enable this register because normally in order that our MCU is the represent of low power MCU family, and we have to enable this register because it's disabled because of the power reduction mode. So actually, that's all the explanation about the task. Right after the meeting, I will create the student folder to allow you to upload the reports, and actually that's all for my side. From my side, in this case, it's quite hard to use the internal simulator and the plotter. You can use the debugger mode to, for example, check the reset the interrupt flag behavior, but normally it's hard to simulate the interrupts behavior in STDD. Hence, I'm giving you the working code, and hence we are in this case analyzing the documentation. Is there any questions about the report or about the technicals, about timers, clocks, etc.? If there is no questions, we have our midterm test on the portal, about 30 minutes. So that's all from my side as for the meeting. If you have any question, ask for the report. Just contact me by email or at my office hours. But this is our first report in the remote lab, so this is quite a simple report, because all you need to do is to analyze this code and refer to the documentation and write some summary, and actually that's all about this exercise. And as I've mentioned, if there's no questions, you can just wait for the test, and we can just end this meeting. As I mentioned, you can leave the meeting if there is no additional question, and just stay logged in on the portal and wait to the 5 p.m. and start the test.
Goodbye.
Thank you.
Thank you. Goodbye.
Thank you. Good.